All right, now we're going to continue studying nilpotent groups. So we're going to assume that G is just a group, a finite group for now. And we're going to assume that G has prime power. Well, you factored its order as a product of n prime powers. So these are n distinct powers. And we're going to let capital P sub I be the CELO subgroup corresponding to the ith prime divisor. Then the following are equivalent. So these are 4 equivalent ways to define nilpotency. So the first one says G is nilpotent, which means, as we saw, that means that you have a this construction, the upper central series is finite. Has finite length. And ends in G. It's worth reminding ourselves what that definition is, because it's worth pointing out in mathematics, whenever you have a statement, a theorem that says the following are equivalent, and one of the statements is G is some definition, then technically a smart mathematician would tell you that any one of the other statements could have been taken as the definition, because they're all equivalent. But for whatever reason, one of the statements ends up being the preferred one, because, well, math has to proceed in a linear fashion. One statement has to be covered first, so some statement has to be given the definition. So the next statement says H is a subgroup of G, then H is a proper subgroup of the normalizer. So note here, the thing that's missing is the bottom line. You want proper subgroup. There's never an equality. So one could have taken this as the definition of normalizer. It is true in lots of areas of math, just for whatever reason, whatever definition they pick is whichever one seems to be the most useful. And it's worth pointing out, although I can't think of an example off the top of my head, there are cases where the definition that first appears in the textbook was not the first definition historically. Actually, I know a very good example. The definition of a group that appears in the textbook was not the first definition. But for finite groups, it's equivalent to the first definition. 3. Your CELO normal subgroups are normal. Your CELO subgroups are normal. And 4, your group is isomorphic to a direct product of its CELO subgroups. So I view 4 as saying that nilpotent groups are a generalization of finite abelian groups, because finite abelian groups can be factored as a direct product of cyclic groups. You sort of have the same feature. You can factor as a direct product, only now the direct product are of the CELO subgroups. And in fact, in a later video, we will prove the fundamental theorem for finite abelian groups, and the first step we use is citing this fact. Abelian groups are nilpotent, therefore, they're isomorphic to the direct product of their CELO subgroups, which are P groups. And so in that context, the fundamental theorem of finite abelian groups reduces to the case of classifying groups of prime power order that are abelian. So these are the 4 different equivalent statements to being nilpotent. And so we'll follow the textbook, which proves 1 implies 2, implies 3, implies 4, and then 4 implies 1. So first, 1 implies 2. So we're assuming G has an upper central series that terminates in G, and we want to prove that for every subgroup that's proper, it's also a proper subgroup of the normalizer. Well, it turns out there's going to be 2 cases. The first case is suppose that the center of G is not a subgroup of H. Well, that means there's something in the center that's not an H. By definition of the center, we have A times little h equals little h times A for all little h in H. Because A commutes with everything in G, therefore commutes with everything in this subgroup, which shows you that A inverse is equal to H. So A is in this normalizer of H and G. So we see the center is a subgroup of this normalizer. That part's actually true in general, but the fact that this element is in the center but not in the subgroup tells us that we certainly have H as a proper subgroup of the smallest group containing H and the center, and that this is a subgroup of the normalizer because it contains H and it contains the center. And the reason why this is proper is because there is an element here that's not in H, namely A. And so in this case, H is a proper subgroup of its normalizer. Note that that holds regardless of whether or not G is nilpotent. So clearly the harder part is when H does contain the center of G. And that tells you this part of the proof will tell you that the counterexample in general is always going to be a subgroup containing the center. Well then, what do? We look at H modulo the center, which is a subgroup of G mod the center. It's worth pointing out G mod the center is nilpotent. So it turns out if I had actually set this up as an induction proof, as long as I assume that size is smaller, then I could apply induction right here to get that H mod the center is contained in this normalizer here, the normalizer and the quotient. Proper subgroup. Of course, by one of the isomorphism theorems, the 4th isomorphism theorem, that tells us that H is a proper subgroup of whatever this is. I could redefine it. There should be an n, so that when you quotient by n, you get this group. And H is a proper subgroup of n. With some thought, you can see by the lattice isomorphism theorems that in fact n is the normalizer in G of H. And so then that would give it to you. H is a proper subgroup of its normalizer. What else is missing in this proof? Well, one would need to rewrite the proof to make it clear you're doing induction. And there's an obvious gap right here that I'm assuming that when you quotient by the center, you get something strictly smaller. And there's another gap that I'm assuming that the quotient is nilpotent. But both these gaps can be filled. So what happens in this case? Well, what happens if you have equality here? Then the center must be trivial. If the center is trivial, then your group is not nilpotent, because you're trying to create this upper central series that terminates in G, and the first group, the series terminates in the trivial group. And the very first two terms are both the trivial group, and therefore the center of this quotient is also trivial. The center of all the Zi groups all become the trivial group. And so if G is nilpotent, this must happen. I also got the idea from a previous video that if G is nilpotent, so is this quotient. And so that fills these two gaps in. There's also the question of what happens when the center is the whole group. Why would that actually matter? Well, if you get down to the trivial group, somewhere, if something breaks, I don't know if it does, but it's worth pointing out there is that special case. If the center is the whole group, then G is abelian, then this normalizer is the whole group anyways. And so the statement becomes a tautology. It says let H be a subgroup of G, then H is a proper subgroup of G. Next, we show 2 implies 3. I'm going to go ahead and actually state what those assumptions are. The second assumption was that every proper subgroup is also a proper subgroup of its normalizer. And the third statement was that every CELO subgroup is normal in G. I mean, one thing you immediately observe, of course, is that PI must be a proper subgroup of its normalizer. So let's see if we can work through all the different consequences. This one actually uses a bunch of different ideas we've covered in this course. So first off, of course, every subgroup is going to be normal in its normalizer. And since this is a proper subgroup, we also can tell that PI is going to be the only subgroup of NGPI of order whatever it happens to be. And so back when we studied characteristic subgroups, we pointed out that if your group had only one subgroup of order D, then that implied that that subgroup was characteristic. Worth pointing out that this normalizer is also normal in the normalizer of itself. So this is a weird argument because you're doing the normalizer construction twice. And we now have PI is characteristic in its own normalizer. then it follows that we had this transitivity property that pi is also normal in the double normalizer. So the whole point of this setup is to show that pi was normal and it's the double normalizer. Why would you want to do such a thing? Because then this will allow you to conclude that the double normalizer is the normalizer and that therefore it's actually all of G. So the whole goal is to give a roundabout way to try to prove that this is actually G. The point here is that since pi is normal in this group, for any x in this group, you have x pi x inverse is equal to pi, which implies that x is in the normalizer of pi. So that tells you that you have equality here. And why would you want equality here? Well, technically this only gives you one of the inclusions, but the other inclusion is always clear. Any subgroup is a subset of its normalizer. And so you have equality. And here we have a problem because remember every proper subgroup is a proper subgroup of its normalizer. And here we have a group is equal to its normalizer. And so by 2, the contrapositive of 2, we have the if you set H equal to this normalizer, what do we see? We see that we have H equal to its normalizer. And so by the contrapositive of 2, we now have H is equal to G. So NG-PI is equal to PI, which by definition of normalizers means that PI is equal to G, which means that PI is normal in G. So the contrapositive of 2 is only used on the very last step. We also see that since we can't actually control in advance how big this normalizer actually was, we actually do see that we need all of 2. We need the statement of 2 to be true for all proper subgroups in order for this contrapositive to be true in this last step. And yes, this is a very, very sophisticated way to prove that something is normal in G. By not actually looking at G at all, but by looking at a bunch of normalizers. Now we show 3 implies 4. This is sort of an induction type of thing, so the induction on T. So remember G as prime factors as a product of prime powers, and the PIs are the CELA subgroups, and the assumption is that each of the PIs is normal in G for all I. And you want to actually show that G is isomorphic to the direct product of the CELA subgroups. What they show first is that actually if you take this product set of the first T CELA subgroups, for the first T primes, you also get a direct product. Prove this by induction, set T equal to N, and that's all of G. Why is this true? Well, PI is normal in G. That at least allows you to conclude that this product is in fact a subgroup. Without that, you can't even get that far. By induction hypothesis, you can assume that P1 through PT minus 1 is isomorphic to this direct product. Let's call this H anyways. And we'll let K be PT. And what do we have? We have K has size P of T, which is PT to the 8T. and H has size P1 to the A1 dot 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 P of T minus 1 to the A sub T minus 1. Notice that these primes are distinct, so they have nothing in common, so it must be the case that H intersect K has size 1. And so, by the theorem about direct products, H times K must be isomorphic to the direct product of H and K. And then using the induction hypothesis, we can replace H with this direct product of T minus 1 groups. And finally, you can drop the parentheses. And so there you have it. As for 4 implies 1, it's probably worth pointing out it'd be an interesting exercise to show that if H and K are nilpotent groups, then H times K is nilpotent. I'll probably assign that in the future as a homework exercise. The book sort of already does it, most of the argument, in this particular context, but it also refers to previous homework exercises that are left to the reader. I mean, the main step, of course, in their proof. And the main step here would be showing that the center of the direct product is the direct product of the centers, and figuring out what happens when you quotient by this center. Then if that's true, you can try using induction on the fact that this is nilpotent and this is nilpotent. I mean, if H and K are nilpotent, then these two groups are nilpotent, and so by induction this product is nilpotent, and use that to build the upper central series for H times K. Admittedly, it's not clear from that explanation why you would need this step, but yeah, you do need this step to prove that step. Assuming these facts are true, well then, we already showed that P groups are nilpotent, and so taking the direct product of P groups is also nilpotent. So if G is isomorphic to a direct product of its P groups, then it has to be nilpotent.